Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to continue further in our series on mathematical models of economics. This is the second lecture in this series, and today we are going to talk on intervals, inequalities and set theory. And for the discussion on the topic, we have with us in our studios Dr. Neeti Bhutani. Dr. Neeti Bhutani is an Assistant Professor in Department of Economics, Hindu College, University of Delhi. Friends, we know that while listening to the lecture, while watching us, you would have lots and lots of questions in mind, and if you feel so that your questions are required to be answered, then you are required to talk to us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. You are just requested to call in the last 10 minutes of the lecture only. Now, I would like to welcome our guest, Dr. Neeti Bhutani, once again. Hello, ma'am. Welcome to the lecture.
Thank you very much, Geetika. Hi, everyone. I welcome you to my second lecture of Mathematical Methods for Economics. In today's lecture, we will go over some mathematical preliminaries which I think are fundamental to your learning. You may have already covered some of these concepts in school, but just to make sure that we are all on the same page, let's revisit these concepts one more time. So, we will start today's lecture with a discussion of inequalities, after which I will take up intervals for discussion. Here I will talk about what a closed interval is as against an open interval, and what a bounded interval is as against an unbounded interval. This is an area that comes under what is known as topology in mathematics, and the terms closed, bounded, etc. are terms that students of economics must be comfortable using. The third topic for our discussion today is set theory. At least I'll get started with it, and we'll see how much we can cover in the time that we have today. With this then as the plan of action, let's get started. In my previous lecture, I talked about the concept of an economic model. And please note here that the emphasis in this course is on the building up of a theoretical economic model. The focus is going to be on theory in this course. Also, I highlighted in my previous lecture that one of the crucial steps in the building of an economic model is one where we introduce notation. We introduce variables and constants which then are connected through equations, inequalities and identities. Now, because you will be coming across inequalities quite a bit in the course of your learning, let us begin by talking about how to work our way through inequalities. We will discuss the rules related to inequalities, but even before that, let me talk a little bit about the symbols that we use when we work with inequalities, and more importantly, how to read those symbols. So please take a look at this slide here. Let us suppose we have two real numbers A and B. Now, as far as the relationship between these two numbers is concerned, A and B can be related in 5 possible ways, and these 5 possible ways are listed here. You can follow the movement of my cursor. The first 2 cases relate to strict inequalities. Strict in the sense that we do not allow A and B to be equal to each other. So when I say that A is greater than B, or when A is strictly greater than B, we write it the way it is written here in the first point in the blue font. Similarly, when I say A is less than B, this means that A is strictly less than B, and it is written the way it is written in the second point here in the blue font. Now the direction of the inequality will get reversed. Then suppose we want to allow for the possibility that the numbers A and B can also be equal to each other. We use weak inequalities which are covered in points 3 and 4. So we have the case where A is greater than or equal to B, which is how you would write things under point number 3. And if A is less than or equal to B, you would write things the way things are written under point number 4. And the final possibility is where A is equal to B, and that of course needs no explanation. Let us get some more language issues out of the way. So when I say A is a positive number, the number A is positive, it means that A is strictly greater than 0. So please note that whenever I say that A is a positive number, I am not including 0 in my discussion. Similarly, when I say the number A is non-negative, it means that A is greater than or equal to 0. And finally, when I say that A is a negative number, this would mean that A is strictly less than 0. So let us get some sense of this term non-negative and how it's where it's coming from. So as I just said, when A is a negative number, that means A is strictly less than 0. So the question here is, what is non-negative or what is not negative? So anything that is not less than 0 would be non-negative, which is to say that anything greater than or equal to 0 would be non-negative. Let us now look at some rules for the manipulation of inequalities. Let us suppose we have the inequality A greater than B, and in turn B is greater than C. Then this implies that A is greater than C. For example, let us suppose the number A is equal to 7 and B is equal to 5. So clearly you can see here that A is greater than B because 7 is greater than 5, and in turn B is greater than C where C is equal to 3. So 5 is greater than 3, which means that B is greater than C. So this will imply that we have this chain of reasoning that A would be greater than C. If A is greater than B and B is greater than C, that implies A is greater than C. So here 7 is greater than 3. Now if we have the inequality A is greater than B, and let's suppose C is any real number, then if I add the number C to both sides of the inequality, I would get A plus C on the left hand side and B plus C on the right hand side. And please note that the direction of the inequality will still remain the same as the original inequality. It will still be towards A. So A plus C will be greater than B plus C. So if we look at the example that we were just working with, our A was 7, B was 5 and C was 3. So if we add the number 3 to both sides of the inequality A greater than B, we would get A plus C, which is 10, which in turn is greater than B plus C, which is in this case 8, 5 plus 3. So clearly A plus C is greater than B plus C. The next rule, and this one and the next one are important rules, so please pay attention. If we have the inequality A greater than B, so you can look at where my cursor is pointing. If we have the inequality A is greater than B, and let's suppose C is a positive number. Positive means strictly greater than 0. And if I multiply both sides of the inequality by the positive number C, then the direction of the inequality will also, in this case, remain the same. So this means that you can multiply an inequality throughout by a positive number. As an example, let's work with the previous set of numbers only. So our A was 7 and B was 5, which is to say that A is greater than B. Now, if I multiply both sides of the inequality by C, which in this case is 3, on the left hand side I'll have AC, which is 21, and on the right hand side I'll have BC, which in this case is 15. So clearly you can see here that AC is greater than BC. However, if I multiply both sides of my inequality A greater than B by a negative number, please note this is very important. If I multiply in the inequality A greater than B, if I multiply both sides of the inequality by a negative number C, then this reverses the inequality. This reverses the direction of the inequality. To see this, let us suppose A is 7 and B is 5 like before. So in this case, A is still greater than B. But let's now suppose that C is minus 3. Okay, so if I now look at A times C, that is now going to be minus 21, excuse me, and BC would be minus 15, 5 times minus 3. But now what happens when you multiply by a negative number? The direction of the inequality gets reversed, because minus 21 is now going to be less than minus 15. So AC is less than BC in general. The last rule that you must be familiar with is as follows. If you have two inequalities, A greater than B and the second inequality is C greater than D, then I can add these two inequalities. So I've written these two inequalities one below the other. If I add these two inequalities, on the left hand side I will get A plus C, and on the right hand side I will get B plus D. This is an operation which is quite commonly used in when you work through various problems in economics, so you should be comfortable with this rule as well. Okay, let's work our way through some inequalities to see how well you have internalized the rules that we just talked about. We will be solving inequalities through what is known as a sign diagram. A sign diagram is actually very useful, and it helps you think through inequalities. It helps you think through what is happening in an inequality in a very systematic way. So please pay attention and please understand how a sign diagram is constructed. So what is a sign diagram? A sign diagram is a diagram that shows the sign variation of the different factors that are involved in an inequality. So if I have an inequality and I reduce it to different factors, then the variation in the signs of those factors is what is reflected in a sign diagram. I'll show you now step by step how this sign diagram is to be drawn, so please pay attention. Our inequality here is, this is what we have to solve for x. It's x minus 3 times 1 minus x is greater than 0. The first step that we have in while drawing a sign diagram is that we plot the critical points. We mark the critical points of the factors involved in the inequality. What is a critical point? A critical point is one where the factor involved in the inequality becomes 0. So let me explain this here. The factors in this inequality are x minus 3 and 1 minus x. So where does x minus 3 become 0? That is x equal to 3. And similarly 1 minus x becomes 0 when x is equal to 1. So as a first step, we will mark the points x equal to 1 and x equal to 3 on our number line. And then we will draw vertical lines from x equal to 1 and x equal to 3. You'll just see in a few slides the reason why we draw vertical lines. These vertical lines actually help us demarcate the regions that we have to analyze for the final analysis of the solution, to find the solution ultimately. Right, so this is the first step. I hope this is clear. Now the second step is one where we introduce our factors. Our factors here are x minus 3 and 1 minus x. These are written here, and we will mark now the regions where these factors are positive and where these factors are negative. The region where a factor is positive, for that region we'll use a solid line, and for the region where a factor is negative we'll use a dashed line. So let's look at the first factor, x minus 3. X minus 3 is clearly positive when x is greater than 3. So if I take a number like 4 or 10, all these numbers would be such that 4 minus 3, for example, would be 1, it's positive, 10 minus 3 is 7. So x minus 3 will be positive to the right of 3. So to the right of 3, we will draw a solid line. And to the left of 3, you can see that if x is less than 3, x minus 3 will be negative. So we'll have a dashed line to the left of 3. Similarly, let's mark the regions for 1 minus x. Now for 1 minus x will be positive when x is less than 1. Because, for example, if x is 0 or minus 1, these are all numbers which are less than 1. So that will make 1 minus x positive. So here to the left of 1, we will draw a solid line. But to the right of 1, 1 minus x is negative, and we will draw a dashed line. The next step. In the third step, we mark the critical points, and depending on whether or not the critical points can be part of the solution, we will use an open circle or a dark solid circle. So here, if you notice, the critical points are 3 and 1. However, if either x is equal to 3 or x is equal to 1, that will make the left hand side of the inequality 0. So we can't have x equal to 3 or x equal to 1 as part of our solution. So what we will do here is we will make open circles at x equal to 3 and x equal to 1 to indicate to ourselves that we are not including these as part of our solution. After this, now we are ready to see how the two factors x minus 3 and 1 minus x interact with each other, and you will now appreciate why we have drawn the vertical lines. So if you see, to the left of x equal to 1, x minus 3 is negative because we have a dashed line there, but 1 minus x is positive. So because our inequality involves a product of x minus 3 and 1 minus x, which is what I am showing in the last step now, the product is going to be negative. Positive multiplied by negative is negative. So we draw a dashed line for the product x minus 3 times 1 minus x. Now between 1 and 3, we see that x minus 3 is negative and 1 minus x is also negative. So the product of the two factors is going to be positive. So we have a solid line between 1 and 3. And finally, to the right of 3, we have x minus 3 positive, but 1 minus x is still negative. So the product x minus 3 times 1 minus x will now be negative. Now, because the question asks us where is this product positive, so we will see where our solid line lies for the last part, and we can see here that our solution will be that x lies between 1 and 3 without including 1 and 3. It's a strict inequality here. So this is how we draw a sign diagram. Let's work our way through another example to see if you've understood how to draw a sign diagram. So this is an inequality where you have to find the solution set for 3x divided by x minus 3 being greater than or equal to 2. Now, before we even get to the sign diagram, as a first step, please note that x here cannot be equal to 3. If you remember what I told you in the previous lecture, division by 0 is not defined. So if x is equal to 3, then the denominator here will become a 0, and that is something which is not defined. So in the first step itself, at the outset, let us rule out x equal to 3 as part of the solution. X can't be equal to 3. Okay. Now the question is, how would you approach this kind of an inequality? How would you work your way through this kind of an inequality? Now, if you are thinking that, okay, one possible way to solve this inequality could be that you cross multiply by x minus 3. If you're thinking of doing something like that, please stop right there. That is something which is incorrect. And why is that incorrect? It is incorrect because if you notice, in the denominator we have x minus 3, the factor x minus 3, which involves our unknown x. Now, if x minus 3 was something positive and you cross multiplied, then there wouldn't have been any problem. But we don't know what x is. So it is quite possible that x minus 3 could be negative, and if you multiply both sides by x minus 3, then that is going to change, that is going to reverse your inequality, the direction of the inequality, and that will simply change the question. So we don't want to cross multiply with a negative number, and here we don't know what x minus 3 is because x is an unknown. So please don't ever cross multiply whenever you have an unknown, because we don't know the sign of the unknown. So how should we go about doing this problem? One way to do this problem is that you can subtract 2 from both sides of the inequality, or you can just take 2 to the left hand side. So that gives us 3x divided by x minus 3 minus 2 is greater than or equal to 0. Right. Now let's make x minus 3 the common denominator, and in the numerator we'll have, after taking the LCM, we'll have 3x minus 2 times x minus 3, and if we open the brackets, we will get on the left hand side 3x minus 2x, which is x plus 6 divided by x minus 3 is greater than or equal to 0. Now that we have reduced our inequality to a set of factors, we are ready to draw our sign diagram. So here you can see our critical points are minus 6 and 3. But remember that because 3 can't be a part of the solution because it involves division by 0, so what we'll do is we'll put a cross at 3. If you notice, I have put a cross at 3 to show that this inequality is meaningless. You can see it here where my cursor is pointing. This inequality is meaningless at x equal to 3, so we'll put a cross. Now you can see the sign variation of the factors also. X plus 6 will be positive to the right of 6, negative to the left of, positive to the right of minus 6 and negative to the left of minus 6. Similarly, x minus 3 will be positive to the right of 3, negative to the left of 3. We'll draw open circles. In this case, we will have a dark circle for x plus 6 because we have a weak inequality. So x equal to minus 6 is always a possible solution because it will satisfy the inequality. So we are going to include minus 6 in our sign diagram here. So we draw a dark circle here, but yes, 3 is not included. So here we'll have an open circle, and then in the final diagram you can see that for the ratio x plus 6 divided by x minus 3, to the left of minus 6 both the factors are negative, so that x plus 6 divided by x minus 3 becomes positive. But then between minus 6 and 3 we have x plus 6 is positive but x minus 3 is negative, so that the ratio x plus 6 divided by x minus 3 becomes negative. And then to the right of 3 you have both x plus 6 and x minus 3 positive, so that the ratio is also positive. Now if you notice, the inequality is asking you where is this ratio x plus 6 divided by x minus 3 greater than or equal to 0. So now all you have to do is you have to look for where your solid lines are in the final analysis, and this is when x is less than or equal to minus 6 or when x is strictly greater than 3. So this is your solution for this particular inequality. Now please note here that when I use the word or, if you look here, the solution says x is less than or equal to minus 6 or x is greater than 3. It means that x is less than or equal to minus 6 or x is greater than 3 or both. So we are looking at, if you're familiar with the concept of the union of two sets, this or means the union of these two sets. X is less than or equal to minus 6 and x greater than 3. We'll work our way through one more example before we start with the discussion of an interval, before I introduce the term interval to you. So here you have to find the solution set of the inequality 2p minus 3 divided by p minus 1 is less than 3 minus p. Here again remember that we will not cross multiply by p minus 1 because P is an unknown and your P minus 1 could very well be a negative number. So please don't cross multiply. Also in your solution, P can't, since we haven't reduced it to factors, let me not talk about this point here at this stage. Okay, so how would you go about working with this inequality? We can add P minus 3 to both sides of this inequality, or simply take 3 minus P to the left hand side, which then gives us 2P minus 3 divided by P minus 1 plus P minus 3 is less than 0. Now we make P minus 1 the common denominator. So taking the LCM, we get 2P minus 3 plus P times P minus 1, which is P square minus P, minus 3 times P minus 1, which is minus 3P plus 3, the whole thing divided by P minus 1, which is less than 0. It's a strict inequality here. Okay, now let's just simplify the terms here. If you notice here, the 3's will get cancelled. This 3 will cancel out this minus 3. Also 2P minus P minus 3P will be P minus 3P or minus 2P. So in the numerator, I now have P square minus 2P divided, which is then divided by P minus 1, and that is less than 0. I can now take P common. So P times P minus 2 divided by P minus 1 becomes less than 0. So now you can see I have reduced this inequality to a set of factors, and we can look at the sign diagram for this particular inequality. So, okay, so here you see that because division by 0 is not allowed, we cannot have P equal to 1 as part of the solution. So, in the final analysis, we would put a cross at P equal to 1 because this makes the inequality meaningless. P minus 1 we cannot divide by 0, and we will talk about this sign diagram, but we'll take a break right now. We'll have to pause this discussion for a short while, and we'll resume this discussion after I get back.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, you're requested to be with us as we are back after a short break and would be discussing more. Till then, be with us. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on in our series on mathematical models of economics, and in our previous session we discussed on inequalities. So in this session too we are going to cover inequalities in detail, and afterwards we are going to talk on intervals and set theory. For the discussion on the topic, we have with us in our studios Dr. Neeti Bhutani. Dr. Neeti Bhutani is Assistant Professor in Department of Economics, Hindu College, University of Delhi. Friends, if you wish to ask questions from Dr. Neeti Bhutani on today's topic, today's session, then do call us through our toll-free number. Our number is 1800-110-430. I repeat, our number is 1800-110-430. Now, I would like to welcome our guest, Dr. Bhutani, once again. Hello, ma'am. Welcome to the session.
Thank you very much, Geetika. Welcome back, viewers. Before the break, we were talking about this inequality. 2p minus 3 divided by p minus 1 is less than 3 minus p, and if you followed my explanation, we reduced this inequality to the factors p times p minus 2 divided by p minus 1 less than 0, and we were about to start with the sign diagram. So let's talk about the diagram now. Right, so we said as a first step that p equal to 1 can't be a part of the solution because that involves a division by 0, and because division by 0 is not defined, we rule that out. We rule out p equal to 1 as part of the solution by putting a cross in the last line. Now, our factors here are p minus 1 and p minus 2. So, let's first plot the critical points of these three factors. For p, the critical point would be 0, for p minus 2 it will be 2, and for p minus 1 it will be 1. We'll again drop vertical lines from all these three critical points. And now let us look at the sign variation of these three factors. So p would be positive to the right of 0, negative to the left of 0, which means that we will draw a solid line to the right of 0, a dashed line to the left of 0. And because it's a strict inequality, we will not be including any of these critical points in our solution. So you can see that for all these factors, we are drawing open circles at 0, at 2, and at 1. Right. Now let's look at the factor p minus 2. P minus 2 is going to be positive whenever p is greater than 2. So we have a solid line to the right of 2 and a dashed line to the left of 2. Finally, we look at p minus 1. P minus 1, for that we would have a solid line to the right of 1 because p minus 1 is positive whenever p is greater than 1, and p minus 1 is going to be negative to the left of 1, so a dashed line to the left of 1. Now let's compare these factors and how these factors interact with each other when we look at p times p minus 2 divided by p minus 1. So to the left of 0, you can see that all three factors p, p minus 2 and p minus 1 are negative, which means that when we let them interact, the term p times p minus 2 divided by p minus 1 would also be negative, because negative times negative would become a positive, which then divided by a negative would mean that that's a negative. But between 0 and 1, we have that p is positive, p minus 1 is negative, and p minus 2 is also negative. So these negatives will cancel each other out, which means that the final expression that we're looking at is going to be positive. Now between the point 1 and 2, we have p positive, p minus 1 negative, p minus 2 is negative, p minus 1 is positive. So overall we get a negative expression for p times p minus 2 divided by p minus 1. And finally, to the right of 2, we have all the factors being positive, so that p times p minus 2 divided by p minus 1 is also positive. Okay, so the question is asking you, where is this expression negative, which means that in the final line here, you have to look for where we have the dashed lines, because that's where p times p minus 2 divided by p minus 1 will be negative. And you can see that to the left of 0, this expression is negative, and also between 1 and 2 without including 1 and 2. So our solution here is going to be p strictly less than 0 or p lying between 1 and 2 with strict inequalities. So this is how you're going to go about solving inequalities. I hope this discussion has been clear and we're all on the same page now. Let's now move on to a discussion of the concept of an interval. Now, to understand what an interval is, let us suppose we have two real numbers. Let's suppose we have two real numbers a and b, and because these are real numbers, you can mark them on the number line. Then an interval refers to the set of all real numbers that lies between a and b. So an interval from a and b would be the set of all numbers that would lie between a and b. Now the points a and b, the numbers a and b, are also known as the end points of an interval. And depending on whether or not the endpoints of the interval are included, so depending on whether both the endpoints are included or neither of the endpoints are included or just one of the endpoints is included, we can distinguish between a closed interval, an open interval, and a half open, half closed interval. So let's take these cases one by one. Let us suppose that both the endpoints are included in your interval. Our endpoints are a and b, and as an example, let's take an interval from 2 to 6 as shown in this slide. Now let us suppose that in the interval from 2 to 6, both the endpoints 2 and 6 are also included in the interval. Then this makes the interval a closed interval. Thus, a closed interval is one that contains both its endpoints. It is represented, for example, in this case by 2, 6, which would then be enclosed in square brackets. Whenever you see square brackets, that would mean that it is we're talking about a closed interval. Alternatively, we could also write a closed interval as the set of all real numbers x, such that x lies between 2 and 6. You can look at this inequality, but because we are including both the endpoints 2 and 6, we'll be using weak inequalities. Now, as a second case, we have an interval from 2 to 6. But now let us suppose we do not include any of our endpoints. We exclude both our endpoints from the interval. So this then gives us an open interval. That is, an open interval is one that does not contain any of its endpoints. So if you look here, the interval here is from 2 to 6 in the second number line, but we are not including 2 and 6 in our interval, and this is therefore an open interval, which is represented as 2, 6, which is enclosed now in simple brackets or parentheses as we call them. Alternatively, we could also write an open interval. We could represent an open interval as a set of all real numbers x, such that x is strictly greater than 2 and x is strictly less than 6. We're taking an intersection here, so it will be an and. Now we also have the possibility where we include only one of the endpoints in our interval, and that then gives rise to what is known as a half open, half closed interval. One possibility here is that we include only the number 2, only the endpoint 2 in the interval, and 6 is not included. So in the interval from 2 to 6, we include all numbers, but we don't include 6. So this is an interval which is closed from the left because we are including 2, but open from the right. So this is a half open, half closed interval. In particular, it is left closed and right open. You can also write it mathematically as the set of all real numbers x, such that x is greater than or equal to 2 and at the same time x is strictly less than 6. The last possibility is where we include 6, the endpoint 6 in our interval from 2 to 6, but we don't include 2. So this is the case of a left open, right closed interval. The next slide shows a generalized description of closed intervals and open intervals in terms of A and B. So I have already explained all these concepts. We can just go over these one more time. So closed interval is represented by, because we're taking the interval here from A to B, so A comma B would be enclosed within square brackets, and both A and B would be included in the interval. The endpoints are included. Similarly, we have the definition of an open interval where we now have a strict inequality. So the only difference here is, I've already explained all this. The only difference here is that instead of 2 and 6, in these formal definitions, we are writing A and B. Similarly, a half open interval is one where you either include B or you either include A in the interval, and the definitions are given here. Now let us define what is known as a length of the interval. The length of the interval is given by the difference between the two endpoints. So in this case it is B minus A, and regardless of whether you have a closed interval or an open interval or a half open interval, the length in all these cases would be B minus A. Which means that if you go back to the example where we took the interval from 2 to 6, the length of that interval would be 6 minus 2, which is 4. Right. We have talked about the distinction between a closed interval and an open interval. The next question is, let us ask ourselves, are the intervals that we've talked about bounded intervals? Now, what do we mean by bounded? Bounded means, can we think of some bounds or some boundaries within which we can get all of our numbers in the interval to lie? Now, the way to think about it is, we can think of, for example, if we take these intervals, we have a closed interval, A comma B, then an open interval, then we have half open intervals. So let me first give you the answer actually. So if I ask, if you're asked, are these intervals bounded? The answer here is yes. All of these intervals are bounded. In fact, it is these endpoints A and B that constitute one set of bounds that can be created for these intervals. Let us see how this happens. So if you look at the first interval A comma B, which is a closed interval, we can think of these endpoints A and B as providing one set of bounds. Please note that these are only one set of bounds. We can have other bounds also, but we're not going into that much detail. Now B can be seen as a bound in the sense that all the numbers in the inequality cannot exceed B. And similarly, A can be seen as a bound in the sense that all the numbers in the interval cannot be lower than B. So here B can be seen as an upper bound and A can be seen as a lower bound, can be viewed as a lower bound. Similarly, in the open interval also A comma B, the endpoints work as bounds or the boundaries that the numbers in the interval cannot cross. Now some of you might ask here, A and B, the endpoints are not included in the interval here. So can we consider these endpoints as bounds? And the answer here is yes. And the way to understand this is as follows. So please hear me out. Let us suppose the house that you live in and your neighbor's house, you both share the same wall. So you have a common wall between the two houses. But let us also further suppose that you got your house built, or whosoever built your house, your house was built after your neighbor's house. In other words, it is your neighbor who got that common wall built. And technically speaking, because your neighbor paid for that wall, the wall belongs to the neighbor. Now, what you see here, even though that wall belongs to the neighbor, it is not part of your house, it still acts like a boundary for your house. So in that sense, we say that B is also acting like a bound. Even though B does not belong to the interval, B is acting like a bound for the particular open interval A comma B. And in the same way, this endpoint A also acts like a bound, in particular a lower bound for the open interval A comma B. And if we look at the half open intervals with the same explanation that we just gave, we can say that the endpoints here also act as bounds. So basically you have that all of these intervals are bounded intervals. In fact, it turns out that as long as your endpoints are finite real numbers, you'll always have bounded intervals. So examples of unbounded intervals include an interval such as this, where x is greater than or equal to a. So an interval going from a to infinity is an example of an unbounded interval. You can see here that one of the endpoints is not a finite real number. That is like a sufficient condition for a bounded interval. Similarly, the second interval, x less than or equal to b, which is the interval where you are going off to minus infinity on the left of b. This is also an example of an unbounded interval. Similarly, if we talk of the real line, so if we talk of an open interval minus infinity to infinity, that is also an unbounded interval. So I hope the concept of bounded closed intervals is clear to you. And we'll introduce one more definition before we move on to a discussion of set theory, which is that when an interval is both closed and bounded, we call it a compact interval. This is a term which is used quite often in economic analysis, so it will be good if you are familiar with it. Right, so that is it as far as intervals are concerned. Let us now start with set theory. I will not be able to complete this topic today in the time that we have, but at least let's get started and we'll see how much we can finish. Okay, so I have been using the term set in this lecture. I've used it and even in the previous lecture, but I did not talk about it in detail, so let's get down to the details now. What is a set? A set is a collection of well-defined objects. So note here, the objects that are part of the set, they have to be well-defined. You can't have vaguely defined sets. And a collection of well-defined objects constitutes a set. These objects are in turn called the elements or the members of the set. The question is, why do we need a set? How is a set helpful or useful to us? And the way to think about it is that a set helps us bring together it helps us group objects of a similar nature. So as an example, let's suppose you want to borrow a novel from your college library and you are interested only in novels by Indian authors. So let's suppose your library has the following Indian authors' books stocked. So you have Amish, Anita Desai, Amitabh Bagchi and Manju Kapoor. So we can define the set, let's call it L. We can define the set L as the set of all Indian authors whose books are kept in your library. And here you can see that we have this common feature, Indian authors, which is being highlighted in this set. A set in particular is represented as by an uppercase letter. So if you notice, in all these examples, I have represented my sets by capital letters, uppercase letters, and the elements of the set are enclosed in curly brackets. This is probably something that you've already done in school. Then we can define the set A as a set of all alphabets. So you can see all the alphabets listed here, A, B, C till X, Y, Z. And in this way, we can define different sets. Now, so far we have said that there has to be some common property between the elements, among the elements, to define a set, but that is actually not necessary. You can also have a set that has some elements which are randomly chosen. So, for example, you have the set G, which consists of the letters A, B, C and the numbers 1, 2. Here there is no common feature in these elements, but they are still elements. They are still elements of this set by virtue of being members of this set. However, if there is some common property that identifies the elements in the set, it is a good idea if you can write that property in a compact form, because that helps you write your set in a compact form. So for example, if I want to talk about the set A, now here the set A represents all the letters of the English alphabet, A through Z. But I can, instead of listing out all of these letters, I can simply write the set A as a set of all elements X such that X is a letter of the English alphabet, which means that here I now don't have to list out each and every element. I can just say that X has a property that it is a letter of the English alphabet. Then similarly, we can define the set I plus, I superscript plus, which is a set of all numbers Z such that Z is a positive integer. This set would then consist of the positive integers 1, 2, 3, 4 and so on, and clearly you don't have to list out the numbers because you have already stated the common property. So this gives you a compact way of writing sets. Then finally, we are talking about the set D, which is a set of all numbers X. You can see my cursor, that's last set. It's a set of all numbers X such that X lies between 0 and 1 with the endpoints included. And if you follow the discussion on intervals, you can note here that this is a closed interval. Right. Now we can distinguish between two kinds of sets, a finite set and an infinite set. And as the terms suggest, a finite set is one that has a finite number of elements, and an infinite set is a set that has an infinite number of elements. So in our examples, in the examples that we were talking about, the sets L, A and G are finite sets. The set L, for example, has 4 elements. It has a finite number of elements. It's a finite set. The set A has 26 elements. The set G has 5 elements, and these are all examples of finite sets. In fact, we use a notation n of the set A to represent the number of elements in the set A. So here our set A is the set of letters in the English alphabet, and here n of A would be 26. Now an infinite set is a set that contains an infinite number of elements. So for example, the sets I plus and D, which we were talking about, let me just go back to one of the earlier slides. So I plus was a set of elements Z such that Z is a positive integer. Here we have the numbers 1, 2, 3, 4 and so on all included. So these are, you have an infinite number of elements in this set, and therefore this is an infinite set. Similarly, the set D also is an infinite set. It's an example of an infinite set because we have an infinite number of points from 0 to 1. Now, if you have studied economics, you will also identify, for example, the budget set as an example of an infinite set. For those of you who have not done economics, let me just quickly walk you through what a budget set is. Let us suppose your pocket money or income is 1,000 and you spend, and it's a too good world, and you spend your pocket money on either Maggie or t-shirts. So X represents Maggie, Y represents t-shirts, and let us assume that the price of Maggie is 20 rupees per packet. I don't consume much of Maggie, so I'm just taking some number at random. And let us suppose the price of one t-shirt is 200 rupees. So if I look at the value of my spending, that will be in general represented as 20x plus 200y, where x comma y represents my consumption bundle, with x representing the number of Maggie packets I buy and y representing the number of t-shirts I buy. So my spending, depending on what my x is and what y is, will equal 20x plus 200y. And clearly the spending that I engage in, given by 20x plus 200y, cannot exceed my income, which is 1,000. So here my budget set has to be the set of all consumption bundles x comma y, such that 20x plus 200y is less than or equal to 1000. And at the same time, we also have to impose the condition, because we can't have negative number of Maggi packets or negative number of t-shirts that you buy. So we'll also impose a restriction that x is greater than or equal to 0 and y is greater than or equal to 0. In other words, x is non-negative and y is also non-negative. So our budget set consists of all the consumption bundles that satisfy these three inequalities. And if we look at a graph, the budget set, if you look at the graph of the budget set, it's going to look like this. It's this region shaded in blue, the region enclosed by the two axes, and this particular line, which is what is called the budget line, which represents all your consumption bundles if you totally exhaust your income. So this is your budget set, which gives you all the feasible consumption bundles that you can purchase given your income and the prices of the two goods, X and Y. And coming back to our main point of discussion, this clearly you can see is an infinite set. So in today's lecture, we talked about inequalities. In fact, I just might devote a whole session to practicing inequalities, just so that you get more comfortable with different kinds of inequalities. We talked about inequalities in the first half of the lecture. We've talked about intervals, and I hope the concepts of boundedness and closedness are clear to you now. In the part that we discussed in set theory, I have introduced two terms, finite and infinite sets, to you. And in the next lecture, we will bring in the idea of what is known as a denumerable and a non-denumerable set. So that is how we will continue in the next couple of lectures. But right now I'm totally out of time. I'll have to end this discussion here. My next lecture is scheduled for July 11, and in that we will talk about set theory in more detail. So do tune in. Bye-bye.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, you are requested to write to us at info.cec@nic.in. This is the ID where you can put in your suggestions as well as your questions too. We'll try to give answers to your questions when next time Dr. Neeti Bhutani visits our studio. Till then, be with us. Keep watching us. Thank you. Thank you, ma'am. Thank you so much.